want to take a look at conic sections on this page. Conic section is described as follows. If you take what's called a right circular cone, you put a circle here like so, and you form a cone in this fashion here, so this is a right angle here, and extend this indefinitely. Then a conic section is what you get if you take this cone and intersect it with the plane. The resulting curve in the plane is called a conic section. And there are several types of these. If the plane is perpendicular to the blackboard here and is parallel to this line that forms the edge of the cone, right, then what you end up with is called a parabola. Right? And its graph looks like this. An example is y equals x squared. Right? So a parabola is such a section. If we take a line that intersects both of these, like this one, a plane that intersects both halves of this, it doesn't go through this center here. We're going to end up with a curve that's got two halves. It's called a hyperbola. Right? And an example is x times y equals 1. Looks like this. If we take now a plane that goes through at an angle here, it goes through at an angle to this main axis of the cone, a central line through the cone, and you intersect this here. As long as this is not perpendicular to this central line, you're going to end up with what's called an ellipse. If it's perpendicular, you can end up with a circle. An example of an equation which describes such an ellipse is x squared over 4 plus y squared equals 1. So that in this case here, when y is equal to 0, x is plus or minus 2 is going to be on this graph. And when x is equal to 0, y is plus or minus 1 is going to be on here. We're going to end up with something that looks like this. Okay. There are other sections that you can get here. For example, we could get a single point by going through the origin here like this, or by going through it like this. So we could have a single point. You can think of that, if you like, as a degenerate circle, a circle without any radius. We can get a line. If we take the plane like so, that just touches the cone on its edge like this, we're going to get one line. If we take the plane that goes through the... Here we're going to get a point. If we take the plane that goes through the center here we're going to get two lines. They'll meet in a point. It's not possible to get two parallel lines, although there's a reason why two parallel lines are also considered to be conic section. So, a parabola, hyperbola, ellipse, possibly a circle, a point, a line, or two lines. All of these, when placed in the plane, have equations that look like this. ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. Here we've taken all powers of x and y of 1 or 2 and linear combination of those and set it equal to 0. All of these are going to have this for their equation. This can also describe two parallel lines. And the empty set. That's to say no graph. And so two parallel lines in no graph are sometimes considered also to be conic sections of trivial conic sections, of course. So we're going to take a look then at parabolas, hyperbolas, and ellipses, starting with parabolas on the next episode. Okay, we now want to take a look at parabolas. Now, we're not going to prove that either parabolas, ellipses, or hyperbolas actually are these conic sections. But a parabola is the section that you get if you intersect the cone in this fashion right here. We want to describe these conic sections in terms of what's called their eccentricity. Parabolas are going to have an eccentricity of 1. And that's defined as follows. We take a point and a line out on the point, and we designate them as focus and directrix. Right. In this case here, we're going to put this focus for simplicity and at least for the meanwhile, at the point P. So P0, and x equals minus P, the other side of the x-axis, is going to be the directrix. Now, what we want to do is we want to consider points x, y, so that when we consider these two distances, d1 and d2, we have the distance to the point, d1, is the eccentricity times the distance to the line, the directrix, d2. For a parabola, d is going to be equal to 1. For any ellipse, it'll be less than 1, and for a hyperbola, it will be greater than 1. All right. So now, we want to consider all the points x, y for this particular directrix and focus so that d2 is equal to d1. Well, what is d2? If this is the point x, y, and this has x coordinates, this line is where x is equal to minus p, then absolute x plus p is the distance to the line, and this is supposed to be equal to the distance of the point, which is square root of x minus p squared plus y minus 0 squared, or plus y squared. We want to put this in more convenient form. Squaring both sides, we get x squared plus 2px plus p squared is equals to x squared minus 2px plus p squared plus y squared. And we've got x squared on both sides, and we've got p squared on both sides, and so we get 4, taking 2px to this side here, we get 4px is equal to y squared. So y squared equals 4px is an equation of a parabola, and what? When x is equal to 0, y is equal to 0, which makes sense here. This distance is this one. The parabola looks like this. This is opening to the right. Right? When you have something like the form y squared is 4px, then you can find what p is, and consequently also find the focus. Right? If you wanted this opening to the left, the equation would be y squared is equal to minus 4px. This opens to the left. The one which opens up is x squared is 4py. Opens upward. The one which opens down is x squared equals minus 4py. So these are equations now for parabolas opening basically to the right, left, up, and down. Right? And the equation is of the form x squared is 4px, y squared is 4px, or x squared is 4py. This type of thing here. And when you've got one like this, you can always find out what p is. Right? We'll take a look at how to graph these. In general, we want eventually to be able to graph anything that looks like ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Right? Now, if we're dealing with a parabola, well, first of all, if we're dealing with a curve that is not rotated, this term here is going to be equal to 0. That's to say, b will be equal to 0 unless there's a rotation. So no rotation. We'll deal with rotation separately later. So if we don't have any rotation, then we're looking at something that looks like this. And if it's going to be a parabola, either A or C is going to be equal to 0. Unless in this case, let's let C be equal to 0. And let's take a look at an example. So, for example, 3x squared plus 4x for D plus 5y plus 6 equals 0 should be an example of a parabola. You're perhaps familiar with this fact here. Well, let's see how to graph it and find the focus and directrix. To do that, what we want to do is take this and complete the square. So I've got 3 times x squared plus 4/3 x. I want to fix this so that I've got a complete square here. And then this is going to be equal to minus 5y plus, or minus 6, huh? So I can write this as minus 5y minus plus 6/5. Right? So I multiply by minus 6/5 by minus 5, I'm going to get minus 6, which will be the correct quantity over there. Right? To complete this square here, oh, I guess I don't want to quite do that yet. Let's just write this as minus 5y minus 6. Let's complete the square here. To complete the square, we divide this by 2, so we get 2/3, and square it, we end up with 4/9. Which means I've added 3 times 4/9 to this side of the equation. So I want to add 3 times 4/9 or 4/3 to the other side. Okay. Now, this becomes then 3 times x minus 2/3, x plus 2/3 actually squared. All right. For the purpose of translating, it's nice to write this as x minus a, because we're going to let x bar be equal to x minus a, in this case here, where a is equal to minus 2/3. Right. This is going to be equal to minus 5y here. Now I want to include the constant with this. We've got minus 6 plus 4/3, so that's going to be minus 18/3 plus 4/3, or minus 14/3. So if we put plus 14 over 3 times 5, 15, this is going to complete the square. Now this is going to be correct here, because we're going to have minus 5 times this is going to give us minus 14/3, which was this quantity right here. Now I also want to write this as y minus a minus 14/15, and I'm going to let y bar be equal to y minus b, where b in this case is minus 14/15. Okay? And what this means then, from the standpoint of graphing this, is that if this is the x coordinate and this is the y coordinates, then at the point minus 2/3 minus 14/15, we can put a center of an x bar y bar coordinate system. So if this is minus 2/3, let's see. X bar is going to be equal to 0 when x is minus 2/3. So this should be minus 2/3 over here, like so. That's going to be the x bar coordinate system at minus 2/3. And the y bar coordinate system, y bar is going to be equal to 0. This is going to be the x, and this is the y bar. The x bar is going to be when y bar is, x bar coordinate here is going to be when y bar is equal to 0. That's to say when y is equal to minus 14/15. So this should be at minus 14/15 here. Y is minus 14/15. And this is the line. X is equal to minus 2/3. Now, if we let x equal minus 2/3 in here, right, then we're going to get, if we replace x minus 2/3 with x bar, we're going to get that this equation is in the form x bar squared is equal to minus 5 times, and we replace this y minus 14/15 by y bar, we're going to get minus 5 y bar, and dividing by 3, we're going to get minus 5/3 y bar. So this now is in the form x squared is 4py. 4p is minus 5/3. So this says that p is equal to minus 5/12. Right? It's the equation of a parabola which opens downward. Okay? Its vertex here now is at the origin of the x bar y bar system. Right? When x is equal to minus 2/3 and y is equal to minus 14/15, this equation is going to be satisfied. It's going to open downward without graphing any more points, something like that. The focus is going to be in the x bar y bar system at minus 5/12. So this is at minus 5/12 in the x bar y bar system. This is an x bar y bar. And the directrix is going to be 5/12 up here. Is going to be up here at 5/12. In the xy system, this directrix is going to be the line y is equals to 5/12 plus minus 14/15. So that's the equation of the line in the xy coordinate system. This point in the xy coordinate system is going to be minus 5/12 minus 14/15. It's 14/15 down here. And the y coordinate is going to be minus 2/3. So this is the focus here. This is the directrix up here. And the graph is going to be something like this. So here we've got something that looks like ax squared plus bx plus ey plus f equals 0, and it ends up to be a parabola. Similarly, if this term was missing, we had a c term, we'd end up with a parabola opening to the right or to the left. If both a and c are missing, we've got an equation of a line. We next want to take a look at the equations of ellipses. Recall that an ellipse is the type of conic section that you get if you intersect this at an angle here through just one side. So either of these two planes will intersect this in an ellipse. It'll be a circle if the plane is perpendicular to the axis here of the of the cone, the center line of the cone. All right. From the standpoint of eccentricity, the eccentricity of an ellipse is less than 1, and this is achieved as follows. We're going to make this convenient for ourselves here, and we're going to put a focus at the point C0. So this is going to be a focus. Right? And a directrix is going to be the line x is equals to c over e squared. This is chosen to make everything work out nicely, and later we will deal with a situation when things are not quite as nice. Now what we want then is to consider the collection of all points xy, so that if we take this distance d1 and this distance d2, d1 is equal to e times d2. And for an ellipse, e is less than 1 for an ellipse. Okay, so we want to write that equation then. This is the point xy here. d1, all right, is the square root of x minus c squared plus y minus 0 squared. This is supposed to be equal to e times the distance from this point to the directrix. Well, the point is xy, and the directrix is at c over e squared. This distance is going to be c over e squared minus x at absolute value. We want to put this in a more convenient form. So then what we want to do with this is to square both sides. Now if we square the left-hand side here, we're going to get x squared minus 2cx plus c squared plus y squared. And this is supposed to be equal to e squared times c squared over e squared minus x. We'll square this. So we're going to get c squared over e to the 4th minus 2cx over e squared plus x squared. Okay. So on the right-hand side here, we've got c squared over e squared minus 2cx plus e squared x squared. On the left-hand side, we've also got minus 2cx. So we can remove those from the resulting equation here and write a new equation. Here we've got x squared, that's minus e squared x squared. So this is x squared times 1 minus e squared. Now we've got a c squared here and a y squared. Let's take care of the y squared. And this is going to be equal to then c squared over e squared. And we still have this c squared to take care of here, so minus c squared. Okay. This right-hand side here now is equal to c squared times what? 1 minus e squared over e squared. So we have this situation right here. And now I'm going to divide both sides by 1 minus e squared, so I've got x squared plus y squared over 1 minus e squared is equal to c squared over e squared. Right? And I want to divide both sides by c squared over e squared. So I've got x squared over c squared over e squared plus y squared over c squared over e squared times 1 minus e squared is equal to 1. And now what I want to do is I want to replace this with a squared, since it's a positive quantity. Since e is less than 1, 1 minus e squared is positive, so this is a positive quantity. I'm going to replace it by b squared. And I'm going to get then for the general equation, x squared over a squared plus y squared over b squared is equal to 1. Equation you've probably seen before. Right? What this means is that when y is equal to 0 here, x is equal to plus or minus a. So that this is the point a, 0 on the graph, and here's the point minus a, 0. Okay? When x is equal to 0, y is plus or minus b. So we get this point 0b on the graph, and also the point 0 minus b. Right? This maybe should be this point over here, because this is symmetric about the this is symmetric about the origin. Well, I guess it's supposed to go through this point right here. So maybe we should make this the point 0b here. It's supposed to go through this point where these distances are right. And over here like so. Not a particularly good drawing, but okay. This is the point 0b. This is the point 0 minus b. A is larger than b. Since A is larger than B, this is called the major axis. And this one right here is called the minor axis. The symmetry here indicates that there's going to be another focus over here and another directrix over here. Note from this that A is equal to C over E. This will allow you to get E, given A and C. Right? A squared is here. A squared times 1 minus E squared is B squared. So we get A squared is equal to B squared plus A squared E squared, and A squared E squared is C squared. So A squared is B squared plus C squared. This is an important one to remember here, where A is the length of the major axis, A is the point of the major axis, and B is the one on the minor. And then we also have the third thing here, namely that the directrix is located at C over E squared. These three equations down here will allow you in general to find out what various quantities are involved with an ellipse. Okay? So here's an example of an ellipse. If it's centered at the origin, the equation looks like this. X squared over A squared plus Y squared over B squared is equal to 1. And these equations are satisfied here by the directrix and the focus and the eccentricity and the numbers A and B. Let's take a look at some ellipses which are centered at the origin and are not rotated about the axes. So that's, for example, x squared over 9 plus y squared over 4 equals 1. To graph this, you can get a quick graph of this by letting x equal 0 and notice that y is plus or minus 2. And there's a point on the graph, and this is a point on the graph. Let y equal to 0, notice that x is equal to plus or minus 3. Now if you draw this box right here, the ellipse will be contained in it. You can get a rough picture of what it looks like by just making a elliptical shape into the box. All right. We want to determine what's happening here, though. What this is 0 to 2, and this is 3, 0, 0 minus 2, and minus 3, 0. A is 3, and B is 2, and we have A squared is equal to B squared plus C squared for the ellipse, where A is the larger of these two here, so that we get C is equal to square root of 5. 9 minus 4 is C squared, so C is the square root of 5. And then the focus is at C, so that's at the square root of 5, which is going to be right about here. Square root of 5, 0. And there'll be a matching focus over here at minus square root of 5, 0. Like so. Now the directrix. A is C over E, and the directrix is at C over E squared. So if we use these two, we'll be able to find what D is. So we find out the eccentricity is C over A, which is the square root of 5 over 3. So less than 1. Right? And then the directrix is at C, which is square root of 5 over E squared, which is 5/9. So this is times 9 over 5. So the directrix is out, what? This is the square root of 5. This is about 4. Directrix is out here. And there's the matching directrix over here, huh? So the directrix at plus or minus here. X is plus or minus. This is one directrix. The minus is one, and the plus is another. So those are the two directrices. Let's take a look at another here. X squared over 4 plus y squared over 16 equals 1. For the sketch, if x is equal to 0, y is plus or minus 4. So 0, 4, and 0 minus 4 are on the graph. When y is equal to 0, x is plus or minus 2. Let's say x squared over 4 is 1, or x squared is 4, x is plus or minus 2. So we can put these 2 points on the graph here. And the resulting ellipsis could look something like this. Now here we need to consider this to be A and this to be B. A is the length, A is the number corresponding with the, well, this is to be A squared and this is to be B squared, huh? And then A squared is B squared plus C squared, so that we get 16 minus 4 is C squared. C is the square root of 12, or 2 square root of 3. 2 square root of 3, square root of 3 is about 1.7, so this is a little more than 3. So here's the focus here, and another focus here. This is the focus at 0, 2 square root of 3. Focus. All right. Again here now, we've got A, B, and C. A is C over E, so that E is C over A, which is equal to the square root of 12 over A is 4. or 2 square root 3 over 4, or square root 3 over 2. So C is that, E is the eccentricity is square root of 3 over 2. Right, that's less than 1 as a check. And now the directrix is at D, where D is equal to C over E squared, which is equal to square root of 3 over 2 divided by E squared, C. C is 2 square root of 3 over E squared, which is 3 over 4. That's to say this is at 8 square root 3 over 3. The directrix is up here at y equals 8 square root 3 over 3. Directrix. And there's another one below. So here are two examples then of ellipses which have their major axis, in this case the x-axis and in this case the y-axis. Take a look at a particular case of an ellipse which is not centered at the origin. We call it ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 is the general equation of a conic, and that b equals 0 here indicates that there's no rotation. We will deal with rotations later. If both a and c are positive or both a and c are negative, then you have a chance that this is going to be an ellipse. That's to say, if a times c is greater than 0, then you're going to have either an ellipse or a point or nothing. Let's take a look at a specific example. Let's look at, say, 3x squared plus 4y squared plus 5x plus 6y plus 7 equals 0. Now I may change the 7 here because it might turn out that we're not actually dealing with an ellipse, but we're dealing with perhaps nothing. To graph this, what you want to do with it is to first of all collect the x terms together and the y terms together and complete the square. So we've got 3 times x squared plus 5x, so that's going to be times 5/3 x, plus we've got 4 times y squared, plus 6/4 y, or 3/2 y, will make this correct, plus, and now this is equals to minus 7. Okay. We want to complete this square here, so you take this term and divide it by 2 and square it. That's to say 5/6 squared, or 25/36 is added on here to complete this square. What have we done? We've added 3 times 25/36, or 25/12. It's not fair to do that. We have to add 25/12 to the other side of the equation also in order to make sure this is still an equation. All right. Here to complete this square, we take 3/2, divide by 2, 3/4, square it is 9/16. We want to add 9/16 on here. That's to say we've added 4 times 9/16, or 9/4. Right? It's not fair to add 9/4 on to both sides without, to that side without adding it on to the other side. So we need to add 9/4 on over here. So what do we end up with all together on this side? Well, we end up with so many 36ths. Okay. 25/12 is 75/36.
4/4 is, what, 81/36? And now we're supposed to subtract 7 from this, and this will give us a negative number. And now what's going to happen is, it's not possible to deal with a negative number. What have we got here? We've got 3 times x plus 5/6 squared plus 4 times y plus 3/4 squared. Okay? So that, what? This cannot possibly, the sum of these two squares times 3 and 4 respectively, there cannot possibly add up to a negative number. So I'm going to change the, what this means is that this doesn't have any graph at all. These two squares add up to a negative number, since there's no x and y. If this added up to 0, then there would be just exactly one point x, y, namely where x is equals to minus 5/6 and y is minus 3/4. I'm going to change the 7 to a 1, so that over here we subtract 1, and here we subtract 36/36, and we get then that this is equals to 75 and 81 is 156, minus 36 is 120/36, so we get net with 120 over 36. Simplifying this, this is going to be what? Dividing by 6, for example, or dividing by 12, we're going to get 10 over 3. So we've got 10/3 is equals to 3. Now I'm going to replace this with x bar. So 3x bar squared plus 4. I'm going to replace this with y bar. 3y bar squared. Right. Now I'm going to rewrite this as x bar squared over 1/3 and y bar squared over 1/4. Now I'm going to divide both sides by 10/3 so that I get a 1 over on this side. Dividing by 10/3, I've got 1/3 times 10/3, and I've got 1/4 times 10/3. Okay? Now, that's to say this is 1 is equal to x bar squared over square root of 10/9 squared plus y bar squared over square root of 10/12 squared is equal to 1. That's the form x squared over a squared plus y squared over b squared is equal to 1. Except now what I've got is x bar is equal to x plus 5/6. It's convenient sometimes to think of this as x minus a minus 5/6. Y bar is equals to y plus 3/4, y minus a minus 3/4. And so if we're graphing this then, this is x and this is y. What? X bar is equal to 0 is going to be the y bar axis. This is the x axis and the y axis. X bar equal to 0 is going to be the y bar axis, and that's going to be when x is equal to minus 5/6. So if we come over here to minus 5/6, we can draw this then as a y bar axis. Right? Y is equal to 0 is y bar is equal to 0 is going to be the x bar axis, and that's going to happen when y is equals to minus 3/4. So if we go down here to minus 3/4, you can draw this as an x bar axis. Right? And now this equation is going to be centered on the x bar, y bar coordinate system. And what's going to happen here? Well, when x is equal to 0, y is going to be plus or minus the square root of 10/12. So when x bar is equal to 0, y is plus or minus the square root of 10/12. That's perhaps here and here. Right? When y bar is equal to 0, x bar is equal to plus or minus the square root of 10/9. It's a little larger than 1, and so that's perhaps over here and here. This then is the picture of the ellipse. Right? Now, what have we got? This is a squared, and this is b squared. And for an ellipse here now, we can get c squared, because a squared is equal to b squared plus c squared. I'm sorry, a squared plus b squared equals c squared. So that c is going to be 10 ninths, c squared is going to be 10 ninths plus 10 twelfths. This is going to equal c squared. So we're now going to be able to compute c. Having c, this will tell us where the focus is. It's going to be at the square root of 10 ninths plus 10 twelfths. We're going to have a focus here and a focus here. I'm sorry, this should be a squared is equals to b squared plus c squared. So this is going to be square root of 10 ninths minus 10 twelfths. Okay, so that's going to give us the foci. And then you have that a is equals to c over e. And this gives us that e is equal to c over a, so that knowing c and knowing a, we're going to be able to get the eccentricity. And finally, d is equal to c squared, is equal to c over e squared. And so knowing c and knowing e, we're going to be able to get the directrix. There will be a directrix over here, and there will be a matching directrix over here. Okay? So using these equations here, I'm not going to do the computations, but you can get the position of the directrix, and you can get the eccentricity. Right? You get c from this equation right here. So this then is an example of an ellipse whose center is not at the origin. Its center is at minus 5/6 minus 3/4. Okay, we want to take a look at another way of describing ellipses. It's as follows. Draw a coordinate system like so, and you consider 2 points, the foci here, at C0 and at minus C0. Then we consider all points xy, so that this distance plus this distance is a constant. Let's call this D3 and D4 here. All right, so what we want is that D3 plus D4 is a constant. And this is going to result in a graph, looks like an ellipse. In fact, you can draw this very easily by putting 2 pins here, making a loop of string with a fixed distance all the way around, putting a pencil in here or writing instrument, and tracing this around here so that these 2 distances always add up to a constant. This is the point, this point right here is the point A0. Then when you compute this constant using these 2 distances, we get that this constant is equals to, what do we have here? We've got 2c plus a minus c and another a minus c. So this is plus 2 times a minus c. Well, this is equals to 2a. Right. So the equation of ellipse, if this indeed gives us an ellipse, is going to be gotten by d3 plus d4 is 2 times a. Let's write that out. What have we got? d3 is the square root of x minus c squared plus y minus 0 squared plus, now d4 is x minus a minus c squared, or x plus c squared, plus y minus 0 squared is equal to 2a. get this in a proper form. That's to say I want to remove these square roots. So if I square this right here, I'm going to get x squared minus 2cx plus c squared plus y squared. This is going to be equals to what I get if I square this side over here. Well, I'm going to get 2a squared, or 2a quantity squared, or 4a squared, plus, what, 4a times this square root, plus this squared. That's to say, x squared plus 2cx plus c squared plus y squared. Okay, on both sides of this equation I've got an x squared term, on both sides a c squared term, and on both sides a y squared term, so I can subtract those from both sides. And if I bring this over to this side here, then I've got minus 4cx, that takes care of these two, is equals to, well, I'm going to subtract the 4a squared from both sides, and I'm going to have plus 4a times this square root. That's this square root right here. And actually what? This ought to be minus, because when I subtract this from both sides, I'm going to get a minus term here. So minus, like so. Okay, this equals minus. Now I can divide through by 4. Divide through by minus 4 for that matter. And now what I'm going to do is square both sides. So on this side here I'm going to get c squared x squared plus 2cxa squared is equals to a squared times the square root squared. That's to say x squared plus 2cx plus c squared plus y squared. Okay. Now what have I got here? Here I've got 2cxa squared, and when I multiply this out, I'm going to get 2cxa squared. So I can remove these two from both sides here, and I will get then c squared x squared is equals to a squared x squared plus c squared plus y squared. Right. Bringing this over to this side right here, or bringing this to this side right here, I'm going to have a squared times x squared minus c squared times x squared. I want to bring a c squared over to this side, so I've got minus c squared plus y squared. Y squared, these terms here should have a squared multiplying them, that's what's missing. This should have plus a squared c squared plus a squared y squared. And multiply this through by a squared, so I should have a squared c squared here, and I should have plus a squared y squared. Okay, now, I want to divide. Oh, there's another term missing here too, right? I'm squaring this right here, so I've got c squared x squared plus 2cx squared plus a to the fourth. So I've got a to the fourth here, and so I end up with a to the fourth over here. Okay. Now we're ready to go here. I want to divide both sides by this quantity, which is a squared minus c squared times a squared. So I'm going to get 1 over on this side, and that's going to be equals to x squared. When I divide by this, I'll be left with a squared plus, when I divide a squared times y squared by this, I'm going to be left with a squared minus c squared. Right. Now, I'm going to call this b squared, which is standard here because b squared now is a squared minus c squared, or a squared is equal to b squared plus c squared. So this now is of the form x squared over a squared plus y squared over b squared is equal to 1. And now these other points here, this is the point minus a0, This is the point 0b, and this is the point 0 minus b. So these are other points than on the ellipse, and this is our standard ellipse with this equation right here describing it. We mentioned one more thing about ellipses here, and that is this. If one takes a point on the ellipse and draws the tangent line to the ellipse, one finds that this angle right here is the same as this angle right here. The angle from the focus to this point and the tangent line, and the angle from the focus to this point and the tangent line are the same. What that means is that a beam of light, for example, directed over to here, will be reflected to the other focus. From one focus, sound or light will be reflected off of here to the other focus. So that, for example, if you've got an elliptical room, a person standing here can hear what a person says over here very clearly, although in between it will not, if this person is even whispering, it will not be possible to hear them. This fact's made use of in making various reflectors and situations where this is a desirable property. Let me mention something here with respect to the parabola. A parabola has this type of reflective property. If this is the focus of the parabola, then if you consider light coming in here parallel, what happens is this angle right here is equal to the angle that the tangent line, the angle that the tangent line makes with a line coming through parallel to that major axis. That angle is equal to this angle here, so that parallel lines will be reflected to the focus. Now this can be used for several purposes. For example, spinning this around, one ends up with something that looks like this, perhaps, and a solar disk, for example, a solar heater. If this is directed at the sun, there will be a lot of heat right here. The same apparatus is used for picking up emissions from satellites, for example, and it's also used in headlights. If a filament is placed right here, all the light is going to be directed out parallel to the major axis, and so that this works for making a good headlight. Right? So this is a property the parabola has, a reflective property, and this is a property that the ellipse has. Right? And here now, there's another way to describe ellipses. If you take 2 points to both sides and make these two distances equal, then the collection of points x, y will form an ellipse. We now wish to consider the third type of conic section here, the hyperbola. And to do that, we're going to do something similar as to what we do with the ellipse. That's to say, we're going to place a focus here at C0. And now we're going to place the directrix at D equals to C over E squared, where E, larger than 1, is the eccentricity. Right? And we wish then to consider all points x, y, so that this distance here to the directrix times E is this distance to the focus. We call this D1 and this D2. Then what we wish to have here is that this distance D1, which is x minus c squared plus y minus 0 squared, or y squared square root, is equals to E times the distance from the point to the directrix, which is going to be absolute x minus c over E squared. Okay, we want to get this in a better form. squaring both sides, we get x squared minus 2cx plus c squared plus y squared is equals to e squared times x squared, well, e squared times x squared minus 2cx over e squared, squaring this, plus c squared over e to the fourth. So like so. Now what happens here? When we multiply this out, we're going to have minus 2cx on this side, and this is going to multiply with e squared to get minus 2cx. So we can remove both of these terms here from both sides, and we end up with then x squared plus c squared plus y squared is equal to e squared x squared plus c squared over e to the e squared. E to the fourth times e squared. Collecting the x squared terms to the left-hand side here, we get 1 minus e squared times x squared, that's these two terms, plus y squared is equals to c squared over e squared minus c squared. Right? We're going to divide everything through by 1 minus e squared, so I'm going to get x squared plus y squared over 1 minus e squared is equals to, if I put this over the common denominator e squared, I get c squared times 1 minus e squared. That's to say this is equal to c squared times 1 minus e squared over e squared. So now dividing by 1 minus e squared gives me c squared over e squared. Now note that 1 minus e squared is negative because e is larger than 1. So I can write this instead of plus this, I can write it as minus y squared over e squared minus 1. Alright? And now I've got x squared here, and what I want to do now is divide both sides by c squared over e squared. So I've got equals 1. This is divided by c squared over e squared. And this is going to be divided by c squared over e squared. C squared over e squared I'm going to call a squared, so this is x squared over a squared. Right? E squared minus 1 is positive, c squared over e squared is positive, so I can call this quantity b squared. It's going to be some number squared. So I write this as x squared over a squared minus y squared over b squared is equal to 1. In which case I get a squared is c squared over e squared, so that a is equal to c over e. That's one important equation here. All right. I can graph this. I can graph a couple points on this fairly simply by letting y equal 0. In which case I get when y is equal to 0, x is plus or minus 8. So I have got these points here, plus or minus a 0, and here would be minus a 0. The graph of this is going to look like this. Okay? It's clear that this thing is going to be symmetric about both the origin and the y-axis here from this equation. And if I draw this point B, when x is equal to 0, y is not defined. But if I draw the point B0 up here, or I'm sorry, 0b, and also the point 0 minus b, and complete this rectangle, right? It turns out that these lines right here are asymptotic to the ellipse. That's to say, this ellipse really doesn't quite look like that. It looks more like this. It gets closer and closer to these lines right here. And this is a a very good aid for drawing it. Similarly over on this side right here. It gets close to these two lines. So more like that perhaps. Okay. There are two other equations that are important here. Right? One of them is this. This is a squared. So we have b squared is equals to a squared times e squared minus 1. Right? That's the same. This is a squared times minus 1, so I'm going to bring that to this side, and you're going to get a squared plus b squared is equal to a squared e squared, and now a squared e squared is c squared. So a squared plus b squared is equal to c squared. So that if you know the equation in this form right here, and you know a and b, you can immediately find c because c squared is a squared plus b squared. Right? You can then find e because a is c over e, and to find d, we have the fact that d is equal to c over e squared. So given an equation in this form here, its graph is going to be a hyperbola, which opens to the right and to the left. Right? We can find the focus by first of all finding c squared, a squared plus b squared is c squared, then finding the eccentricity. That will give us c, the focus, and we can find the eccentricity, because the eccentricity is c over a, and then we can find the directrix, it's going to be c over e squared. There's going to be another focus because of the symmetry over here, or we can consider there being a focus over here, and another directrix over here. So there's the formula for hyperbola opening to right and left and centered at the origin. Now I want to take a look at some specific examples of hyperbolas which are centered at the origin. So first I'll take a look at, let's say, x squared over 16 minus y squared over 9 is equal to 1. Right? And graphing this, what? When y is equal to 0, x is plus or minus 4. So we can plot those 2 points real easily. There's this and this one. Now, when y is equal to 0, x is plus or minus 4. When x is equal to 0, y is not defined. But if we looked at y equals plus or minus 3, and draw this rectangle like so, this is going to be an aid in drawing the hyperbola, because if we draw these lines like this, the graph of the hyperbola is asymptotic to those lines, so the hyperbola should look something like this. But just by applying these 2 points and the asymptotes, it's possible to get a pretty good representation of what the graph of this hyperbola looks like. This is a squared, and this is b squared. Right? And a squared plus b squared is equal to c squared, so that c squared is 25, and c is equal to 5. So the focus for this is at 5, 0. This point A is forward 0, and by symmetry here, there's another focus at minus 5, 0. And this point here, of course, is minus 4, 0. All right, so we now have C. A is C over E, so that E is C over A, which is equals to 5/4. Right? Good check here. This is larger than 1. This is the eccentricity of of this particular hyperbola. And now D is equals to C over E squared, which is to say it's equal to 5 over 25/16. So 5 times 16 over 25. It's at 16 over 5, or 3 1/5. So right here is the directrix. I'll add 3 1/5 over here, and then there's a similarly there's a directrix over here at minus 3 1/5. So there's a picture of the graph of this particular hyperbola. Let's look at another. Well, let's look at one with the other direction. Y squared over 9 minus x squared over 4 is equal to what? When x is equal to 0, y is plus or minus 3. So we can draw these 2 points here easily. Plus 3. Minus 3. And now if we draw x is plus or minus 2 in here, and complete this rectangle, it's going to allow us to draw in the asymptotes to this graph. And now with these 2 points here, we can now draw a pretty accurate picture of this, the graph of this hyperbola. Looks like this. It has to be asymptotic to those 2 lines. Right. This point right here is the point 0, 3. And this point here is 0, minus 3. Supplying those 2 points in the 2 lines, we then have a pretty good picture. We want to look at the rest of this though now. Now this is the other way around. So this is a squared here, and this is b squared here. Right? And a squared plus b squared is equal to c squared. And so we have that this is equal to 81 and 16. No, I'm sorry, 9 and 4, 13. C squared is 13. And so consequently C is the square root of 13. So we have a focus here then at the square root of 13. It's a little more than 3. So this is 0, comma, square root of 13. This point here is. And another focus matching down here at 0 minus the square root of 13. Now for the directrix, well, first the eccentricity. A is c over e, so that e is equals to c over a, which is equals to square root of 13 over 9. Oops, over 3. A is 3. Square root of 9. A squared is 9. Right? So the eccentricity is a little more than 1. That's a good check. Right? Then the directrix is at c over e squared, which is going to be square root of 13 over 3 divided by, oops, I'm sorry, c, which was square root of 13, divided by e squared, which is 13 over 3. So this is going to be 3 square root 13 over 13. We'll end up with a directrix then that's right around here. And by symmetry here, another directrix over here. So this is D is equals to 3 square root 13 over 13. The line y equals D. Okay, so then here are 2 pictures of hyperbolas. One over to the right and left, the other one up and down, and both with their center at the origin. which is not centered at the origin. Again here, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 is the general equation of a conic. Here b equals 0, so there's no rotation. And now this will be a hyperbola if a and c are of opposite sides. That's to say, if a times c is less than 0. So let's take a look at a specific example. Let's look at the analogous one to the ellipse that we considered. That's to say, 3x squared, now minus 4y squared, plus 5x plus 6y plus 1 equals 0. Okay? Again, here we want to collect the x terms together. We're going to get 3 times x squared plus 5/3 x. Right? And the y squared terms here, we're going to get minus 4 times y squared, 6/4, we have minus 6/4, or 3/2 y. And this is going to be equal to minus 1. To complete this square, we divide by 2, get 5/6, so we have to add 25/36. Right? That's to say we've added 25/12 to this side, we have to add 25/12 to this side. To complete this square, we get 3/4, we square it, we get 3/4, we square it, we get 9/4. We've added 9/4 to that side. We've added, we subtracted 9 over here, huh? We subtracted 9 from this side, so we have to add 9. Subtract 9 from this side. Okay. So all together here then, what have we got? We've got 3 times x plus 5/6 squared minus 4 times y minus 3/2 squared something's wrong here. This is 3/4. Right? When we square, we should get 9/16. Okay. So this is eventually going to be 3/4 squared, and now we've subtracted 9/4 from this side, so we have to subtract 9/4 from the other side, giving us all together here then, huh? So many 12ths. What have we got? 25/12. We've got minus 9/4. All right. So 9/4 is going to be 27/12. So this is going to be minus 27/12. And then we've got minus 12/12. Right? So 25 minus 27 is minus 2. We end up with minus 14/12 or minus 7/12. Minus 7/6. Minus 2/12 minus 14/12 is minus 7/6. So this is our equation then. And then if we let this be equal to x bar, and this be equal to y bar, we have x bar squared and y bar squared. We have divided by 1/3. We have divided by 1/4. This is minus. I now want to divide by minus 7/6. So So I'm going to get 1 over on this side. I'm going to get minus here. I'm going to get times minus 7/6 here, so or times 7/6. And this minus sign here, when I divide by 7, minus 7/6, I'm going to get 7/6 in the denominator here, and a plus sign here. Okay, so this is equal to y squared over 7/24, y bar squared over square root 7/24 squared, that's this, minus x bar squared over a third times 7/18, so square root 7/18 squared is equal to 1. Okay, so this is the equation of this in the x bar, y bar coordinate system. Okay, let's take a look at that. If this is x and y, then what do we have here? If we write this as x minus a minus 5/6, we get that x bar is equal to 0 when x is minus 5/6. That's to say the y bar coordinate system, the y bar axis is at minus 5/6. So here's y bar. And this is at minus 5/6. X equals minus 5/6. The x bar is going to be at 3/4. That's to say when y bar is equal to 0, y is 3/4. So that's going to be over here. If this is 1 unit again, then at 3/4, we're going to have the x bar coordinate system. So that here's the center, the origin of the x bar coordinate system. Now, what happens to this? When x is equal to 0, y is plus or minus the square root of 7/24. Right? That's to say, what? That's approximately a half. So in the y bar coordinate system, we go up here to the square root of 7/24, like so. And down here to the square root of 7/24. And these are 2 points, 0, square root 7/24, and 0 minus square root 7/24 are 2 points in the x bar y coordinate system, y bar coordinate system on the graph of this. If we now graph plus or minus the square root of 7/18, that's again less than 1, something like so. If we complete this rectangle, we will get, and now this is just a rough picture here, we will get these for asymptotes, and the graph of our hyperbola is going to look something like this. And likewise up here. Okay. Now from this we can compute, this is A, so this is A squared, and this is B, so this is B squared. And from this we can compute C squared is equal to A squared plus B squared. So this is 7/24 plus 7/18. So we get C is equal to the square root of that. And once we have C, A is at C over E. So that E is C over A. So we can get the eccentricity from here. Right? And the directrix is going to be at C over E squared. Right? We've got C and we've got E. We'll be able to find the focus and the directrix. The focus for this particular picture is going to be approximately there and there. Directrices are going to be here and here. And you can then compute their values in the xy coordinate system if you want them. That's to say we can compute this, for example, this point right here, 0 square root 7/24. Right? In the x bar, y bar coordinate system is what? To get the x coordinate, we have got to add what? 3/4. So we have 3/4. No. X bar is at, the center here is at -5/6 3/4. Right? So to get this point in the XY coordinate system, it's 0 here, so it's going to be -5/6 in the XY coordinate system, and here it's square root of 7/24. So we have to add 3/4 to that to get what it is in the XY coordinate system. So it's going to be bigger in the XY coordinate system by 3/4 than it is in the X bar coordinate system, this point right here. So this point, we can compute it in the XY coordinate system, as we can with any of the other points. The foci or the directrices, we can recompute these in the XY coordinate system once we've found them in the translated system. So here's an example of a hyperbola whose center is not at the origin. Take a look at another way of describing hyperbolas now. It's as follows. Draw the axes like here, and like this, and put two foci here. One at C0, and the other one at minus C0. We then consider all points xy beyond the hyperbola. If this distance, the difference between these two distances is a constant. So if this is D3 and this is D4, then what we want is absolute D3 minus D4 is a fixed constant. Now, one of the points on here perhaps is going to look something like this. We're going to designate this point as the point A0, and we can find out what this constant has to be here. Namely, by the fact that this is the distance here, like so. It's C plus A, right? And that minus this distance here, distance to the other focus, which is C minus A, right? It's supposed to be equal to constant. Well, this is 2A. So the constant is 2A, and so we get D3 plus D4 is equal to 2A, describes what we're going to want for our hyperbola. I'm going to draw this in here as I expect it to look, namely like so. We'll see if that's the case. Let's write this out. This is not D3 plus D4, it's D3 minus D4. Right? D3 is, well, I guess for the picture I've drawn here, this is the absolute value is going to be D4 minus D3, so let's do that computation. D4 minus D3, that'll give us this right half here. Actually, when we square both sides of this several times, we'll get both halves of this. At any rate, D4 is going to be this longer distance here, and so it's going to be x plus c squared plus y minus rho squared y squared square root. This minus square root of what? X minus c squared plus y squared. This is supposed to be equal to 2a. Okay, what we want to do is we want to bring this to the other side of this equation and square both sides so we get this in a better form. When we do that, we're going to get x squared plus 2cx plus c squared plus y squared is equal to, now we've got this positive on this side of this equation here, so when we square this, we're going to get 4a squared plus 2a times the square root, this square root, plus the quantity inside here squared, which is going to be x squared minus 2cx plus c squared plus y squared. Okay, so that all together here then, we've got x squared on both sides here, we've got y squared on both sides, we've got c squared on both sides. So we can remove those quantities from this equation and rewrite it. Bringing the minus 2cx over here, we get 4cx. That takes care of this term right here. Minus 4. Whoops, this should be twice the center term here, so this should be a 4a. So this is, so now minus 4a squared is equals to 4a times the square root here, huh? X squared minus x minus c quantity squared plus y squared. We can cancel the 4's throughout here. We want to square both sides again. In which case we're going to get c squared x squared minus 2a squared cx plus a to the 4th is equals to a squared times x squared minus 2cx plus c squared plus y squared. So we're on both sides. Right? And now here we've got minus 2a squared cx, and over here, when we multiply this out, we'll have minus 2a squared cx. So we're going to remove both these terms from this equation, and we're going to get then c squared x squared plus a to the 4th is equal to a squared x squared plus a squared c squared plus a squared y squared. Collecting these terms to the x squared terms to the right here, we've got a squared minus c squared times x squared. That's these two terms here. Plus a squared y squared, takes care of the term with the y in it, is equals to a to the 4th minus a squared c squared. Right? When I divide both sides by this so that I get 1, over here when I divide by this, this is a squared times a squared minus c squared, so I'm going to get x squared over a squared. And now I've got plus y squared over a squared minus c squared is equal to 1. Now, a is less than c, so that a squared minus c squared is negative. So I can write this then as 1 equals x squared over a squared minus y squared over c squared minus a squared. Okay? And I'm going to let c squared minus a squared be equal to b squared, so that finally here I get x squared over a squared minus y squared over b squared is equal to 1. With b squared equals to c squared minus a squared. Or as before, a squared plus b squared is c squared. So this is the same equation that we had before. All right? A couple of things to note here are that the hyperbola also has a reflective property. And the reflective property is as follows. If there's a beam that tends toward this focus over here, it will be reflected off. Let's say this angle and this reflected angle will be equal, so that it heads toward the other focus. And while we're at it here, let's take a look at what's needed to compute the asymptotes for this. That's to say, if this is an asymptote, and this is an asymptote, like so, then this line right here is the line y equals, this is the point 0b, example, this, it has, for its equation, x squared over a squared minus 1 is equal to y squared over b squared. If you take the square root of both sides here, we get that y is equals to, or y over b, is equal to the square root x squared over a squared minus 1, right? So that y is equal to b times this. One line is plus b and the other line is minus b times this. So this is the equation of the plus part is the equation of the upper part of the hyperbola. This is the equation of this line. And what we want to know then is that if we take the equation of the line, b over a times x, and we subtract the equation of the hyperbola, b square root x squared over a squared minus 1, right? And we take the limit here as x approaches infinity, then that this is equal to 0. Right? Now, this is a little bit tricky to do, and I'm not going to do it, but you can get this by considering this part here to be a capital A, and this part here to be a capital B, and then this is A minus B. And now if you multiply and divide by A plus B, you will get the result of this limit. Multiply this quantity by capital A plus capital B, so that you get A squared plus B squared, and the square root will disappear here. You will then find that this limit here can be computed, and then it's equal to 0. And so these are indeed lines asymptotic to the graph of the hyperbola. Okay. So here is another way to look at the hyperbola. It's the collection of points x, y, so the difference between these two distances is a constant. Right? And this shows that this is the same as what we had before. We want to now take a look at what happens if you write things with respect to a new coordinate system which has been rotated. For that purpose, let's let this be the xy coordinate system, and let's consider rotating this through an angle alpha here to form a new coordinate system, the x bar, y bar coordinate system. Now let's now consider a point here, the point being xy in the xy coordinate system. Right? And let's suppose that this point makes an angle theta here with the x bar, y bar coordinate system. Then what do we have? Right? If its distance from the origin is r, then we can get its x bar and y bar coordinate system. The x bar and y bar coordinates, x bar, the x bar coordinate is going to be equals to r cosine theta, and y bar is going to be equals to r sine theta. Likewise here, its x coordinate is going to be equals to r cosine of alpha plus theta, and its y coordinate is going to be equal to r sine of alpha plus theta. Now, using the formula for the cosine of the sum of two angles, you get that the x coordinate here is going to be equal to r times cosine alpha, let's multiply this out to 2, cosine alpha cosine theta minus times r